Hello, I'm Bori from Zhejiang University. Today I'm going to talk about how we bring WebAssembly to IoT applications integrated with cloud servers. In 2017, WebAssembly is proposed by major browser vendors such as Google and Apple. It is a binary instruction format that can be compiled from various programming languages such as C, Rust, and Go, and can directly run in browsers. So with WebAssembly, many developers port their client applications such as Photoshop and Google Earth to the web with their existing code bases. By design, WebAssembly is a common compilation target of various languages and could run on different hardware architectures. Moreover, it achieves near-native performance due to its compact binary design and continuous optimization by the community. With these two advantages, WebAssembly now goes beyond the web and is widely used as the backbone of cloud services, such as serverless computing and cloud-native applications. These applications are supported by independent WebAssembly runtimes such as Node.js, Wasmer, and Wasm 3. Nowadays, Cloud IoT integrated applications extend the ability of the cloud and plays an important role in our daily life. So if we go one step further, bring WebAssembly from the cloud for cloud IoT integration, what would it be like? However, we found this adoption is not easy because of the limited RAM on IoT devices. We investigate the hardware resources on popular IoT devices in this figure. These devices can be separated into high-end and low-end ones. However, none of the existing WebAssembly runtimes can run all the devices. Node.js, Wasmer, and WAMR could only run on high-end IoT devices due to the limited RAM. Wasm 3 is the state-of-the-art lightweight WebAssembly runtime. It can only serve on several low-end IoT devices, also due to the limited RAM. Toward this challenge, we propose WAIT to enable better cloud IoT integration. Our goal is to facilitate seamless WebAssembly execution, especially on resource-constrained IoT devices. Firstly, I would like to show how to develop and run a cloud IoT integrated application with WAIT. With the help of the cross-language nature of WebAssembly, developers can write their application logic using their preferred languages. Moreover, because WebAssembly is not specifically designed for IoT applications, it does not natively support IoT-specific tasks such as peripheral accessing. So WAIT fills this gap with APIs tailored for these tasks. With these APIs, developers can express their complete application logic for both cloud and IoT. Then the developer's application is compiled to WebAssembly and can run on the cloud server. The WebAssembly module can also be distributed to the IoT device if necessary, such as when the module needs to read sensors. On the device, WAIT has an ahead-of-time runtime to first compile WebAssembly to native code for efficient execution. Then, a binary-level optimizer optimizes the energy consumption of the generated binary. WAIT also leverages compile time and execution time safety checks. This is because under the cloud IoT integration scenario, the WebAssembly module is transmitted over the insecure networks and is vulnerable to network-based attacks. The key design of WAIT is the lightweight ahead-of-time runtime of WebAssembly for resource-constrained devices, and we'll elaborate on it for the rest of this talk. If you are interested in details of binary-level energy optimizers and the safety checks, you can find them in our paper. Okay, now we move on to how WAIT enables efficient execution of WebAssembly on resource-constrained IoT devices. Before we dive into the details of our runtime, we first give a full view of the three methods to execute WebAssembly. The first and simplest approach is interpreted execution. It has the smallest RAM usage, but its execution speed is the slowest. Just-in-time runtimes compile the frequently executed code to the native during the interpretation to achieve better execution speed. Ahead-of-time compilation first compiles the whole WebAssembly module to native assembly and then runs it. In general, it performs the best in speed, but it requires the most RAM usage to run a full compilation. So we are thinking about which approach fits better for the IoT scenario. The just-in-time compilation is widely used in the browser. This is because the users of browsers would like to see contents immediately, while the AOT compilation takes a while before execution. Moreover, opening website is not a long-running task. Users may only interact with it for only a short time, so a slower execution is acceptable. However, IoT applications are usually long-running and do not update frequently, so the runtime efficiency is the most important thing, and the ahead-of-time compilation is acceptable. Thus, we think IoT compilation is more suitable for IoT applications. This leads to the next question: how to reduce the unacceptable RAM usage of IoT compilation on IoT devices? As we talked about before, the IoT compilation contains a compilation stage and an execution stage. We optimize this RAM usage for both stages. During the compilation stage, existing runtimes read the whole WebAssembly module into RAM and compile it. This approach incurs unacceptable RAM usage. So we wonder if we could use streamed IoT compilation for WebAssembly modules. However, this streaming approach is not directly adaptable due to the special block design of WebAssembly. In WebAssembly, the control flow is organized into blocks. As shown in the right code snippet, there are two blocks, and the branch instruction BR1 means jump to the end of the first outside block. In this example, it is the line 11. However, in the assembly of constrained IoT devices, the target of a branch instruction is only a definite address, such as BRK on the AVR platform means jump to K instructions later. This causes problems for the streamed compilation. When we try to compile the BR instruction, the jump address is unknown due to the end of the block is not reached. So in wait, we propose a streamed lookback compilation. During the IoT process, wait recalls a set of block states, such as the depth and exit address. When we run into a BR instruction, we temporarily recall its current location and its destination depth, and then continues compiling. When finished the compilation of the whole block, wait look back at the incomplete branch instructions and fill the destination address. This streamed lookback compilation significantly reduces the RAM usage and makes the AOT compilation on resource-constrained IoT devices feasible. However, when we enter the execution stage, another problem arises. The memory of WebAssembly is organized into a linear memory region. Originally, wait invokes the compiled WebAssembly module, and the linear memory is placed in the heap. But the heap on constrained IoT devices is limited and the linear memory cannot fit. We re-examined the RAM layout during the compilation and execution. We found that some data in the data and BSS section is unnecessary after the AOT compilation, such as the variables we use for streamed lookback compilation, the cache of global function address, and the cached compiled instructions. While some wait variables are still useful after the compilation, such as the variables kept for receiving new WebAssembly modules. Thus, we leverage a post-compile memory trimming to free the unnecessary RAM usage after compilation. But the useful and useless data intertwine with each other. How can we separate them? In wait, we first create a new section named wait and assign the useful data to it. Then, after the AOT, we treat the data and BSS section to leave more space for the linear memory. This memory trimming technique facilitates most applications run on IoT devices, but some of the applications still have difficulty to run. The problem is introduced by the constants. In IoT applications, especially on constrained devices, some of the calculations are implemented by a table lookup. This is a trick of IoT developers to trade space for execution time. Existing WebAssembly runtimes have no optimizations for IoT scenarios and directly load all the data into RAM. This makes the data-intensive applications not executable. So we would like to borrow the compiler optimizations on constants of IoT devices and move the constant to the flash, because the flash is usually more abundant compared with RAM. Fortunately, WebAssembly organizes the constant data in a separate data section, as shown in this figure. So during the AOT, we check if the RAM usage of generated application fits the device. If not, wait will excerpt the constant and save them in the flash. In the compiled code, wait will generate the stubs to retrieve data from the flash and leverage a jump table to save the absolute addresses of the remapped constants. The jump table is placed in the wait section and is available during the compilation and execution. This approach significantly reduces RAM usage, especially for complicated applications. Moreover, wait does not perform this remapping for all the applications because accessing the flash is much slower than RAM and will lead to performance degradation. Now we use the stream lookback compilation, memory trimming, and constant remapping to enable efficient and lightweight AOT compilation on WebAssembly on resource-constrained devices. We then evaluate how wait performs under real-world applications. As we said earlier in this talk, our goal is to enable efficient execution on all IoT devices. So we choose the IoT board that has the most limited resources. That's the ATmega 128P board with only 4 kilobytes of RAM. We use 6 benchmarks containing simple application, typical data processing application, and a real-world IoT application that tracks the heat source using a set of heat sensors. It has a calibration phase and a detection phase. First, we evaluate the compile time memory footprint of wait. We compare wait with 3 baselines: direct native execution, an AOT compilation named WAMR, and a WebAssembly interpreter version 3. We use a red line to denote the 4 kilobytes RAM limit of the evaluation board. We can see from the figure that wait achieves more than 80 times RAM usage against the existing AOT runtime WAMR. Even compared with the interpreter, wait can also achieve a 13 times reduction against version 3. According to the IETF terminology, constrained IoT devices are divided into 3 classes: C0, C1, and C2. The C0 devices only have less than 10 kilobytes of RAM. We can see from the RAM footprint across compilation and execution stage that wait is the only runtime to run WebAssembly on C0 constrained devices. To better illustrate how the 3 RAM optimizations of wait contribute, we present a detailed breakdown of the compilation and execution stage. First, without stream lookback compilation, all the 6 benchmarks are not executable. Then, during execution, complicated benchmarks are not executable due to their RAM requirement is too big, such as heat detection and FFT. With our memory trimming technique, the FFT benchmarks becomes executable, while the 2 heat detection benchmarks are still not, because of the large constant lookup tables in the application. These 2 benchmarks are even not executable under the native execution environment. The constant remapping facilitates the execution of these 2 benchmarks. Before the end of this talk, we want to discuss the design choices and limitations of wait. First, we like to discuss the optimality of the streamed AOT compilation. The existing compilation infrastructures such as LLVM read the whole module into RAM and analyze it and perform several optimizations and then compile it to native. Most of the optimizations depend on the control flow graph of the application and are not available during streamed AOT compilation. To run on resource-constrained devices, we trace the optimality of the generated code for resource usage. It is worth noting that if the target device has enough resources, we could also switch to the full binary compilation with optimizations such as existing works using LLVM. The second design choice we want to discuss is why not have the AOT compilation in the cloud and directly disseminate the compiled WebAssembly module. The most important reason is portability. Usage scenarios such as mobile agent computing and V2X applications require the application module shuttles among several heterogeneous devices. If the module is AOT compiled in advance, the server will have to store all the versions of the application and cannot achieve seamless computation offloading, especially when the devices only owns a peer-to-peer connection to other devices and are not directly connected to the cloud. Finally, we'd like to discuss the usage scenarios of WAIT. In general, WAIT is suitable for all the cloud IoT integrated applications, especially when the application involves heterogeneous instruction set architectures. Moreover, if the developers of an application are from diverse programming language backgrounds, such as developing an IoT application using serverless function chains from multiple languages, WAIT is also suitable for this scenario. Alright, to sum up, we present WAIT, which brings WebAssembly for seamless cloud IoT integration. WAIT could achieve more than 80 times less RAM usage than the state-of-the-art system, and we open source the implementation of WAIT on GitHub. We want to give our special thanks to our Shepherd for his constructive advice, though the advice helps a lot to improve our paper. WAIT is merely a small initial step for bringing WebAssembly to the IoT domain, and we envision more applications and research could build on top of it. Thank you all for your listening.